Two particles can be linked across the universe in perfect, silent conversation. This is quantum entanglement, a real phenomenon so strange that Albert Einstein called it spooky action at a distance. By the end of this journey, you will understand how this instant connection is reshaping our concept of reality itself. We will uncover how observing one particle can dictate the state of its partner millions of light years away, and explore whether the fabric of space and time is an illusion. What does it mean for our universe to be so deeply interconnected? Einstein could not accept a universe built on dice rolls. In 1935, he co-authored a paper with Boris Podolsky and Nathan Rosen, a thought experiment designed to expose the absurdity of quantum theory. They argued that if the theory were correct, it would lead to what he famously called spooky action at a distance. This was the EPR Paradox, a brilliant attack on the heart of quantum weirdness. Einstein believed in a rational, local reality, where objects are only influenced by their immediate surroundings, and where information cannot travel faster than light. The idea that measuring one particle could instantly change another, even if it were on the far side of the galaxy, violated this core principle. It seemed to suggest that the universe was somehow interconnected in a way that defied space and time itself. For Einstein, this was proof that quantum mechanics, however useful, was an incomplete picture of a deeper, more orderly reality. On the other side of this intellectual battlefield stood Niels Bohr. He defended the quantum description not as a flaw, but as a fundamental feature of nature. For Bohr, the universe was not a clockwork mechanism, but a web of probabilities and potentialities. This was not merely an academic debate. It was a profound clash of worldviews, a battle for the soul of physical reality itself. Why did the greatest mind of his era find this idea so deeply unsettling? Because it challenged the very notion of a universe that exists independently of our observation. The EPR paper forced physicists to stare into the abyss of their own equations, and many did not like what they saw. It set the stage for decades of heated debate, a conflict that revealed a truth far stranger than anyone had anticipated. Accepting entanglement required a conceptual revolution, one we are still grappling with today. This historical struggle is the essential prelude to understanding how such an outlandish idea could ever be proven real. So what exactly is linked across that vast distance? The answer lies in a property like polarization, the direction a light wave oscillates. Picture creating a pair of photons, the fundamental particles of light, in a special way so that their fates are intertwined from the very moment of their birth. Before anyone looks, before any measurement is made, neither photon chooses a polarization. It's not that the answer is hidden, it's that the question hasn't even been asked yet. Each photon exists in a shimmering haze of maybe, a superposition of every possible polarization state at once. The magic, the true entanglement, is in the correlation between their maybes. Their individual uncertainties are perfectly tied together. If you measure one and find it vertically polarized, its partner, no matter where it is in the universe, instantly snaps into a horizontal polarization. The relationship is fixed, even if the individual identities are not. This is the heart of it. We are not watching one particle send a faster-than-light message to the other. There is no signal, no energy, no force traveling between them. Instead, they behave as if they are two parts of a single, deeper entity, described by one unified quantum recipe. They share a single existence, a shared identity that completely ignores the space between them. This foundational idea of a non-local connection forces us to ask, how could we possibly prove something so bizarre is real, and not just a flaw in our thinking? The debate between Einstein and Bohr seemed destined to remain a philosophical stalemate, an argument over the interpretation of equations that could never be settled by experiment. That changed in 1964 with a quiet, unassuming physicist named John Stuart Bell. Bell devised a brilliant theorem, a kind of mathematical litmus test that could finally determine who was right. He drew a line in the sand known as Bell's inequality. Any universe that operates on Einstein's terms, with local hidden variables where particles have secret, predetermined plans and no spooky actions, must always obey this rule. But if the quantum description were correct, if that spooky connection were real, then experiments would show a clear violation of Bell's rule. The math was unambiguous. The universe had to choose a side. The challenge then fell to experimentalists to build a device that could ask nature this direct question. The most famous of these efforts was led by Alain Aspect in the 1980s. His team created pairs of entangled photons and sent them flying off in opposite directions toward detectors. The genius of the experiment lay in its speed. The detectors could switch their measurement settings randomly, and crucially, they switched so fast that not even a signal traveling at the speed of light could communicate between them in time. This closed the locality loophole, the last hiding place for any common-sense explanation. There was simply no time for one particle to whisper its secret to the other. When the results came in, they were definitive. Bell's inequality was violated repeatedly and conclusively. The universe had answered, and it had chosen Bauer and quantum weirdness. This was not merely confirming a theory. It was eliminating a whole class of intuitive, common-sense realities. There were no hidden plans. The particles' connection was instantaneous and fundamental, a basic ingredient of our cosmos. This experimental validation transformed entanglement from a philosophical curiosity into a hard, undeniable physical fact. It forced the entire physics community to accept that our universe is not locally real. The comfortable, classical world we experience is a facade, and beneath it lies a realm where things are deeply, mysteriously, and instantly connected. So if there is no hidden information and no signal, what mechanism could possibly allow for such a profound connection? Einstein's discomfort strikes at the very foundation of physics, a direct collision between two of our most successful theories. His own theory of relativity established the speed of light as the universe's ultimate speed limit, a rule woven into the fabric of space and time. Nothing with mass can ever reach it, and nothing, not even a whisper of information, is permitted to travel faster. This is not a suggestion. It is a cosmic law, the bedrock of cause and effect. Then along comes quantum entanglement, presenting what looks like a blatant violation. One particle is measured here, and its partner, millions of light years away, responds instantly. It appears to be the ultimate loophole, a way to send a signal that defies distance and time. This was the core of Einstein's spooky action. It was not merely strange. It was, to his mind, illegal. How could the universe possibly allow for such a thing without tearing causality itself to shreds? The resolution to this paradox is found in one of quantum mechanics' most clever safeguards, the No-Communication Theorem. This is the crucial caveat that saves relativity from being broken. While the correlation between the particles is indeed instantaneous, you cannot use it to send a single bit of information. Think of it like this. You are in a room with one of the entangled particles. You decide to measure it. The result you get is completely random. You might find it spinning up or spinning down, but you have absolutely no control over the outcome. It is like flipping a coin that was minted at the moment of entanglement. You cannot force it to land on heads to mean yes or tails to mean no. The person with the other particle, no matter how far away, also gets a random result. On its own, their measurement is just another coin flip, meaningless without context. The magic, the correlation, only reveals itself later, when you both get on a slow, subliminal phone call and compare your notes. You say, "I got heads at exactly this time," and they reply, "Incredible, I got tails at that exact same moment." The connection was instantaneous, but the message about that connection plods along at a speed slower than light. So relativity's cosmic speed limit remains unbroken. The universe, it turns out, is weirder than even Einstein feared, but it is also brilliantly adept at upholding its own most fundamental rules. It allows for a deep, instantaneous connection that does not transmit a single word. This leaves us with a profound and unsettling question. If no information is being exchanged, what kind of connection are we actually witnessing? This profound connection is what physicists call non-locality. It is the radical idea that two objects can be instantly linked without any force or energy crossing the space between them. This is not the familiar action at a distance we see with gravity or magnetism, where a field permeates the cosmos to exert a pull. Non-locality is something far more fundamental. It suggests that the entangled particles are not truly separate entities at all. To grasp this, consider a simple pair of gloves. Imagine you have a box containing one left-handed glove and one right-handed glove. You take one box to Earth and send the other to Mars without looking inside. When you open your box on Earth and find a left-handed glove, you know instantly that the glove on Mars is right-handed. But this is just a matter of hidden information. The gloves had their handedness all along. They were just waiting to be revealed. Quantum entanglement shatters this simple logic. In the quantum realm, the gloves do not have a definite handedness until you look at one. Before observation, they exist in a fuzzy state of being both left and right-handed simultaneously. The very act of you opening the box on Earth and finding a left-handed glove is what forces the glove on Mars to become right-handed at that exact moment. There was no pre-existing plan. Your local action defined a reality across a vast, interplanetary distance. This is the core of the mystery. It challenges our most basic assumption about the world, that objects have their own properties regardless of whether we are looking at them. Non-locality implies that what happens here is not independent from what happens there. The universe seems to operate as an interconnected whole, where the idea of separate locations can, for entangled systems, become a kind of illusion. If distance is not a fundamental barrier for this deep connection, then what does that tell us about the nature of space itself? So if space is not a barrier, what is it? The answer may lie in one of the most audacious ideas in modern physics, a proposal that stitches together the two great pillars of our understanding. It is called the ER equals EPR conjecture. This elegant equation, proposed by thinkers like Juan Maldacena and Leonard Susskind, suggests that the spooky connection of entangled particles and the cosmic shortcuts known as wormholes are not just related. They are, in fact, two different ways of describing the very same thing. On one side, EPR represents the entangled pair, those two particles linked across any distance. On the other, ER stands for the Einstein-Rosen bridge, a theoretical tunnel through the fabric of spacetime, a wormhole. The conjecture boldly states that these are one and the same. Those two entangled particles are not magically communicating. Instead, they are connected by a microscopic wormhole, a geometric shortcut so tiny it operates at the Planck scale, far beyond our current ability to see. In this breathtaking view, the spooky action is not an action through space at all. It is a direct link via the geometry of spacetime itself. The vast emptiness separating the particles is an illusion. They are, in a very real geometric sense, neighbors. This turns our intuition inside out. We perceive a universe of vast, lonely distances, but at its fundamental quantum level, it may be a densely woven tapestry, crisscrossed by an unimaginable number of these tiny bridges. Every instance of quantum entanglement could be a thread in this cosmic fabric, a microscopic stitch in the architecture of reality. This leads to a stunning reversal of logic. We usually think of space as the stage upon which things like entanglement happen. But what if the stage itself is built from the actors? The ER equals EPR idea implies that space-time and gravity might not be fundamental. Instead, they could be emergent phenomena, large-scale illusions that bubble up from a vast, underlying network of quantum entanglements. The smooth continuum of space and time we experience would be like the surface of a lake, a calm, collective behavior emerging from countless microscopic interactions happening beneath. This is more than just a clever solution to a quantum puzzle. It is a potential pathway to a theory of everything, a way to finally reconcile the rulebook of the quantum world with Einstein's description of gravity and cosmic geometry. It hints that the key to understanding the universe's grandest structures, from black holes to the cosmos itself, is written in the language of its smallest, most intimate connections. This shift in perspective turns the entire mystery on its head. We are no longer just asking what entanglement is, we are beginning to ask what it can do. In the burgeoning field of quantum information science, entanglement has stopped being a philosophical puzzle and started being a practical tool. It is treated not as a ghostly paradox, but as a tangible resource, as concrete and usable as electrical power or a stream of digital data. This is the fuel for a coming technological revolution. The core of its power lies in a specific quality, a form of correlation that is fundamentally stronger than anything possible in our everyday, classical world. Imagine you and a friend are trying to coordinate on a task with a set of instructions. In the best classical scenario, you might have a prearranged plan or a walkie-talkie to communicate. But with entanglement, it is as if you both share a single, unified mind for that specific task. Your actions are coordinated not by sending messages back and forth, but by this deeper, instantaneous link. This quantum advantage is not about doing things a little faster. It enables forms of processing and security that are impossible for any conventional computer or communication system. By meticulously manipulating these entangled states, scientists and engineers can now perform computations and send messages in ways that were once pure science fiction. This paradigm shift, from asking what it is to asking what we can build with it, signals a profound maturation. Quantum physics is no longer just a description of nature's strangest behaviors. It is becoming an engineering discipline with blueprints and prototypes. Seeing entanglement as a resource is the essential first step toward harnessing its raw potential. A potential that finds its most dramatic expression in the world of quantum computing. That potential resource we call entanglement becomes the very engine of a new kind of machine. At the heart of every quantum computer lies a simple but profound unit of information, the qubit. Unlike a classical bit, which is a definitive 1 or a 0, a qubit can exist in a state of superposition, embodying both 1 and 0 at the same time. This is like a coin spinning in mid-air, a whirl of potential heads and tails. But the true, transformative power does not come from a single spinning coin. It emerges when you have many of them, all perfectly entangled. This is where the magic happens. When qubits are entangled, their fates are woven together. The state of one instantly influences the state of all the others, creating a single, unified, and exponentially complex quantum state. It is as if you have not just a handful of spinning coins, but an entire galaxy of them, all spinning in a perfectly coordinated dance. This entangled network allows a quantum computer to explore a staggering number of possibilities all at once. Think of searching for a single, unique sentence in a library containing every book ever written. A classical supercomputer would have to walk down each aisle, pulling every book off the shelf and checking it one by one. This process could take longer than the age of the universe. A quantum computer, by contrast, uses its entangled qubits to effectively read the spines of every single book in the library simultaneously. It does not check them one after another. It checks them all at the same time. This massive parallelism is what gives quantum computers their phenomenal speed for very specific, but incredibly important, tasks. Factoring astronomically large numbers, a problem that underpins the security of our digital world, becomes tractable. Simulating the intricate behavior of a new drug molecule or a novel battery material, something that would choke even the most powerful supercomputers, becomes possible. Entanglement is the invisible glue that binds all these qubits into a cohesive computational whole. Without this instantaneous, non-local connection, a quantum computer would just be a chaotic collection of individual, probabilistic bits, each doing its own thing. It is the coordinated power, orchestrated by entanglement, that makes the system revolutionary. This foundational role solidifies entanglement not as a ghostly paradox, but as the indispensable cornerstone of the next computational era, a resource we are only just beginning to learn how to harness. While the quantum computer uses entanglement to explore countless possibilities at once, that same phenomenon provides a shield of absolute security. This is the domain of quantum cryptography, a system where the very act of spying announces its own presence. The most famous method is known as quantum key distribution. Imagine two people, traditionally called Alice and Bob, who need to share a secret. Alice begins by sending Bob a stream of individual photons, each one prepared in a specific quantum state representing a piece of their secret code. She might polarize a photon vertically for a 1 or horizontally for a 0. But here is the quantum twist. She can also use two other diagonal bases, rotating the entire system. So a 1 could be a vertical photon or a photon polarized at 45 degrees, depending on the random basis she chooses for each bit. Bob, on his end, has his own detector, and for each incoming photon, he must randomly guess which basis to use for his measurement. Was this photon sent in the vertical-horizontal basis or the diagonal one? Only if he guesses correctly does he get the right bit value. After the transmission, Alice and Bob get on an ordinary, unsecured phone line. They openly discuss which basis they used for each photon, but not the result they got. They keep only the bits where their bases matched, and they discard all the others. This synchronized sifting process leaves them with a perfectly random, secret string of ones and zeros, a key that only they share. This key can then be used to encrypt a message with absolute security. But what stops an eavesdropper, let us call her Eve, from simply intercepting these photons and reading them? This is where the magic of quantum mechanics creates an unbreakable seal. At the heart of this security lies the no-cloning theorem, a fundamental law of the quantum world. It is impossible to create a perfect, independent copy of an unknown quantum state. Eve cannot simply grab the photon, copy its information, and send an identical one along to Bob without him knowing. She is forced to measure it, and just like Bob, she has to guess which basis to use for her measurement. If she guesses wrong, which she will do half the time, she irrevocably changes the photon's state. She might measure a diagonally polarized photon with a vertical-horizontal detector, forcing it to randomly become either vertical or horizontal, completely destroying its original information. When Bob later measures this now altered photon, there is a high chance his result will not match what Alice originally sent. Later, as a final check, Alice and Bob can take a small sample of their secret key and compare the bits over the phone. If they find even a single discrepancy where they should perfectly agree, they know with certainty that someone was listening in. The entire key is compromised and they simply discard it and start over. The security is not based on a mathematical puzzle that might one day be solved. It is guaranteed by the physics of measurement itself. Eavesdropping is not a stealthy operation. It is an act of vandalism that leaves clear footprints. This moves the goalposts of security from computational difficulty, which can be overcome with more powerful machines, to a fundamental physical principle. The fragility of quantum superposition, the very thing that makes it so strange, becomes its greatest strength for protecting our most sensitive information. Beyond securing individual messages, entanglement promises to weave a completely new kind of global web. This is the vision of a quantum internet, a network where entanglement itself is the currency of communication. It would not simply move data faster. It would unlock capabilities that are fundamentally impossible for our current internet. The backbone of such a network relies on a remarkable device called a quantum repeater. Ordinary internet signals weaken over long distances and are boosted by repeaters that copy and retransmit the information. But you cannot copy a quantum state. A quantum repeater works differently. It acts as a trusted intermediary, creating two separate entangled pairs, one with you and one with your intended recipient far away. Through a delicate quantum operation called entanglement swapping, the repeater can then link these two pairs, forging a fresh entanglement between you and the distant party without the fragile connection ever having to travel the entire distance at once. It is like splicing two short ropes together to make one long one without ever moving the entire rope. By daisy-chaining these repeaters, we could theoretically create a web of entanglement spanning the entire globe. This infrastructure would enable something extraordinary: distributed quantum computing. Separate quantum processors in different cities, or even on different continents, could be linked into a single, vastly more powerful computational entity. They would pool their qubits through entanglement, working in perfect, instantaneous concert to solve problems too immense for any single machine. The applications ripple out from there. Imagine a national voting system where your ballot is not just encrypted, but encoded into an entangled state. Any attempt to tamper with the vote count would be instantly detectable, guaranteeing the integrity of the election. Financial transactions on a quantum internet would be settled with absolute, physics-guaranteed security. Or picture a network of quantum telescopes, each one an ultra-precise atomic clock or sensor, all entangled across the planet. This would create a single, planet-sized instrument of phenomenal accuracy, capable of detecting gravitational waves with unimaginable clarity or mapping underground resources with pinpoint precision. The grand challenge, the engineering mountain we must now climb, is learning to share this fragile quantum connection reliably across thousands of miles. Building the quantum internet is not an incremental upgrade. It is one of the great technological endeavors of our century, a project that aims to weave the spooky connections of the quantum world into the very fabric of our global society. This process of forging new connections from old ones has a name: entanglement swapping, and it is the ingenious trick that could one day weave our quantum web. It allows us to entangle two particles that have never met, never shared a source, and never been in the same room. Picture two separate, independent pairs of entangled particles. Let us label the first pair A and B, and the second pair C and D. They are two distinct, isolated friendships. Particles A and B are linked, and particles C and D are linked, but there is no connection between the two groups. Now, bring particles B and C together to a special kind of laboratory, a device that performs what is called a Bell state measurement. This is a joint operation that does not simply look at B and C individually. Instead, it probes the very nature of their relationship, forcing them to reveal their combined quantum identity. This act is decisive. In that instant, particles B and C become inextricably linked by the measurement. But here is the beautiful, counterintuitive consequence. That act of linking B and C does not break their original bonds. It transfers them. At the very moment the measurement on B and C is completed, their distant partners, particle A and particle D, suddenly, instantly, become a new, perfectly entangled pair. Think of it like a social network. B and C are two people who meet for the first time. They have a deep, meaningful conversation, a joint measurement. This single interaction is so profound that it causes their best friends, A and D, who have never even heard of each other, to suddenly become the closest of friends. They are entangled, their fates now perfectly correlated across any distance, all because of a single local interaction between their mutual contacts. This is not just a neat trick. It is the fundamental mechanism for building a scalable quantum internet. We cannot send a fragile entangled state from New York to Tokyo in one go. The connection would decay, but we can create a chain of shorter, robust links. A short link from New York to Chicago, another from Chicago to Denver, a third from Denver to Los Angeles, and so on. At each node, a quantum repeater performs entanglement swapping, splicing these short links together to create one continuous, long-distance entanglement between the endpoints. This process reveals something profound about the nature of entanglement itself. It shows us that entanglement is not merely a static, unbreakable bond between two specific objects, forged at their birth. It is a dynamic, relational property that can be transferred, a kind of quantum correlation that can be handed off from one set of particles to another. The universe, it seems, is far more fluid and interconnected than we ever imagined, capable of creating deep, instantaneous relationships out of thin air. If we can master this handing off of quantum connections, what other hidden potentials might we unlock? This strange ability to hand off connections challenges our very experience of time. We live in a world where cause always comes before effect, where a broken glass cannot reassemble itself. This is the arrow of time, an irreversible flow from past to future. But does quantum entanglement respect this arrow? The answer is deeply puzzling. The correlations themselves appear to be symmetric in time. Imagine setting up an experiment with an entangled pair. In one laboratory, a scientist measures her particle. In another lab, far away, her colleague measures the partner. From our everyday perspective, one measurement happens first and causes the other. Yet, if you were to analyze the quantum math, the situation is curiously reversible. The outcome of the measurement seems to influence the state of its partner, regardless of which measurement is performed first in a given reference frame. This is not about sending a signal. It is about a deep, logical consistency that defies a simple timeline. The two events, the two measurements, are so perfectly correlated that the idea of one causing the other begins to break down. They are simply two aspects of a single, unified phenomenon. To make sense of this, some physicists have proposed a radical idea called the transactional interpretation. In this view, the act of measurement sends a wave forward in time, an offer. But to seal the deal, a confirmation wave must travel backward in time from the future outcome. These waves, traveling in both temporal directions, meet and reinforce each other, settling on a single, consistent history. While this does not allow for practical time travel or sending messages to the past, it implies that at the quantum level, the distinction between past and future might be blurrier than we think. The deep connection forged by entanglement seems to exist outside of our linear experience of time. It hints that time itself, the relentless flow we feel in our bones, could be an emergent property, a large-scale illusion that arises from a more fundamental, timeless quantum reality. The universe may not be a movie playing in one direction, but a completed tapestry where every thread is already woven into place. The moment of measurement is the quantum world's great mystery. We have this entangled system, a shimmering cloud of potential where both particles exist in a linked state of maybes. Then we look. One particle snaps into a definite reality, and its partner, impossibly far away, does the same. But what force, what event, draws that line between possibility and fact? What exactly triggers this instantaneous collapse of the wave function? This is the measurement problem, the deepest and most stubborn puzzle at the heart of quantum theory. It is not a question of what happens, but when and why. Is the decisive moment when a photon strikes a silicon detector, when a needle moves on a dial, or does it require the subtle flicker of a conscious mind to to finally crystallize reality from the haze of probability. The equations of quantum mechanics describe the blurry quantum state with perfect precision, but they are utterly silent on this point of transition. They offer no recipe for what qualifies as a measurement, leaving a gaping hole in our story of how the world works. This ambiguity has forced physicists to propose radically different interpretations, each painting a different picture of what becomes of our entangled connection. The traditional view, known as the Copenhagen interpretation, takes a pragmatic stance. It says the collapse is a fundamental, irreducible process. The act of observation by a macroscopic, classical instrument forces a random choice. One possibility is actualized, and all the others vanish forever. In this view, the entangled connection truly does snap at the moment of measurement. It is a clean, decisive break, a random but final transition from the quantum world to the classical one we perceive. But another compelling idea, the many worlds interpretation, rejects this notion of collapse entirely. It argues that the wave function never collapses. Instead, when you measure an entangled particle, you do not force a single outcome. You become entangled with the system yourself. The entire measuring apparatus, your sense organs, and your conscious awareness all become part of one vast, correlated quantum state. In that moment, the universe branches. One version of you sees the particle spin up and continues into a future where that was always the result. Another version of you, just as real, sees it spin down and walks a different path. The connection between the particles did not snap. It proliferated, weaving itself into the fabric of two newly separate realities. In one world, the correlation holds one way. In the other branch, it holds the opposite way. The link is eternal, but the observer has been split in two. So, is the universe a place of single, random facts, or a constantly branching tree of parallel realities? The answer changes everything about the nature of that instantaneous connection. If Copenhagen is correct, then each measurement is a moment of genuine creation, a tightening of the cosmic weave that severs one thread to define another. If many worlds is true, then nothing is ever severed. The quantum connection simply expands, embracing everything that interacts with it, creating an ever-growing multiverse where every possibility is realized. Both interpretations account for the experimental results, but they tell profoundly different stories about the underlying nature of existence. This tells us that our grasp of quantum mechanics, for all its predictive power, is still incomplete. We have the rules of the game, but we are still arguing about what the board looks like, and who, or what, is really moving the pieces. The fate of the entangled connection is inextricably tied to this grandest of questions: the mysterious transition from the quantum realm of potential to the classical world of definite experience. This fragility of entanglement leads us to the central villain in our quantum story, the phenomenon of decoherence. It is the relentless process that explains why your coffee cup does not exist in a superposition of being both on your desk and on the moon. An entangled state is a delicate whisper in a world shouting with noise. Every interaction with the surrounding environment, from a single photon of light bouncing off a particle to the faintest tremor of a vibration or the whisper of a magnetic field, acts as an inadvertent, unintentional measurement. These interactions are not malicious. They are simply the universe constantly poking and prodding at everything within it. When an entangled system is exposed to this environmental noise, its precious quantum coherence begins to leak away. The perfectly synchronized dance of the entangled particles becomes desynchronized, their shared quantum state dissolving into the chaotic background. The superposition collapses not because a scientist decided to look, but because the entire world is constantly, clumsily, looking all the time. This is why the inner sanctum of a quantum computer resembles a sci-fi fortress. To protect these fragile quantum states, engineers must create an environment of almost absolute stillness. The quantum processors, the qubits, are housed in massive dilution refrigerators that cool them to a fraction of a degree above absolute zero, a temperature colder than the void of deep space. This frigid environment slows atomic motion to a near standstill, minimizing thermal vibrations. They are also suspended in ultra-high vacuum chambers, creating a void emptier than the space between planets to prevent collisions with air molecules. Every stray photon must be blocked, every external electric field shielded. This immense effort is all a single, continuous battle against decoherence. It is not that the laws of quantum mechanics cease to apply to large objects like cats or cars. The mathematics governs everything. It is that for any object large enough for us to see, the quantum properties, the superpositions and entanglements, are instantly and completely washed away by trillions upon trillions of environmental interactions every second. Their quantum nature is erased before it can ever be noticed. Decoherence is the veil that separates our solid, predictable classical reality from the probabilistic quantum weirdness simmering just beneath the surface. Overcoming this relentless enemy, learning to protect our quantum whispers from the classical roar, is the single greatest engineering challenge standing between us and the full promise of a quantum future. This invisible quantum connection can now be measured. We have a mathematical tool to weigh its strength, a concept known as entanglement entropy. This is not the familiar entropy from thermodynamics, which describes the disorder in a gas or the heat in an engine. Instead, it is an information theoretic entropy, a precise measure of the quantum information shared between two parts of a system. Think of a simple entangled pair of particles. Their entanglement entropy is high, signifying a deep, intimate sharing of quantum knowledge. They know everything about each other. But what does that really mean for an observer? If you were to hold just one of the particles in your hand, completely isolated from its partner, this entropy would quantify your ignorance, the sheer surprise you would experience upon learning the state of the distant particle. It measures the missing information you have about the whole system by only looking at one half. This tool transforms entanglement from a simple yes or no question into a rich, scalable quantity. We can now ask not just if two things are linked, but how much. This has become a revolutionary lens for examining the universe's deepest puzzles, most notably the nature of black holes. Through the holographic principle, physicists have made a staggering discovery. The entropy of a black hole, the amount of information it can contain, is not proportional to its vast interior volume as you might expect. It is proportional to the area of its event horizon, its two-dimensional surface. It is as if all the information about every star, planet, and atom that ever fell into that cosmic pit is not lost in the depths, but is somehow painted, pixel by pixel, onto its spherical boundary. Entanglement entropy is the mathematical language that describes this. The fabric of space itself, according to this view, may be woven from a dense network of these quantum entanglements across this surface. The connection we see between particles is a microscopic thread in this grand cosmic tapestry. By giving us a way to measure the amount of connection, entanglement entropy allows physicists to treat this spooky action as a tangible, quantifiable resource, one that may ultimately write the rules for gravity and the very storage of information in our universe. The implications of this quantum tapestry reach far beyond our laboratories, stretching to the very edges of the cosmos. Could it be that the entire universe was once a single, colossal quantum system? To find out, we must look back to the very beginning, to a fleeting moment known as cosmological inflation. In the first fraction of a second after the Big Bang, the universe underwent a growth spurt of unimaginable speed, expanding faster than light itself. During this violent birth, the vacuum of space was not empty and calm. It was a turbulent sea of quantum fluctuations, tiny ripples of maybe and perhaps. As space stretched at a fantastic rate, it stretched these quantum ripples along with it, inflating them from the microscopic to the cosmic. The tiny, random jitters that once governed particles were blown up to become the seeds for galaxies, galaxy clusters, and the entire cosmic web we see mapped across the sky today. But here is the profound part. These fluctuations, the very blueprints for all structure, are thought to have been deeply entangled with one another. The universe in its infancy was not a collection of separate, independent points. It was a unified, coherent whole, its parts connected by the same spooky links we now study in the lab. This primordial entanglement has been stretched and diluted over billions of years, its delicate coherence shattered by decoherence on a cosmic scale. Yet, physicists believe its faint ghost might still be visible. They search for its subtle signature imprinted in the oldest light in the universe, the cosmic microwave background radiation. This afterglow from the dawn of time is a snapshot of the infant cosmos, and hidden within its minute temperature variations could be a whisper of that original, universal connection. This idea extends even to the empty space around us. Quantum field theory tells us that the vacuum is not truly empty. It is a seething, bubbling foam where pairs of virtual particles spontaneously pop into existence, dance together for an impossibly brief moment, and then annihilate each other. For that fleeting instant, these particle pairs are entangled. The vacuum, therefore, is not a void. It is a dynamic medium, constantly stitching and re-stitching itself together with an unimaginable number of these microscopic, temporary entanglements. This paints a breathtaking picture of our reality. The cosmos is not a collection of objects placed within a passive stage of space and time. It is an active, dynamic entity that is fundamentally quantum and non-local at its core. Entanglement is not just a strange phenomenon that happens within the universe. It appears to be a fundamental ingredient that was woven into the fabric of space-time from the very first moment. The space between stars is not a true emptiness, but a dense, living fabric held together by countless quantum threads. This radical vision pushes our quest to its ultimate limit, forcing us to ask how we could ever test such a grand and all-encompassing idea against the cold, hard data of observation. To push quantum entanglement to its absolute limits, we must take our experiments out of the laboratory and into the cosmos itself. This new frontier aims to close one of the most stubborn loopholes, the freedom of choice loophole. The concern is subtle but profound. In Earth-bound experiments, when scientists randomly choose which property of a particle to measure, could that choice itself be influenced by some hidden variable? A secret signal from the past that predetermined both the scientist's decision and the particle's behavior, creating only the illusion of spooky action. To slam this door shut for good, physicists are turning to the oldest light in the universe. One ambitious proposal involves using distant quasars, brilliant cores of ancient galaxies, as cosmic random number generators. Here is how it would work. Researchers on Earth would create a pair of entangled photons. As these particles speed toward their separate detectors, two giant telescopes would swing into action. Each telescope would fix its gaze on a different quasar, billions of light years away. The specific polarization, or orientation, of a single photon arriving from that quasar would be used to decide, at the very last instant, how to measure the entangled particle here on Earth. The beauty of this scheme lies in its cosmic pedigree. The light from those quasars has been traveling for billions of years, long before the entangled pair was even created in the lab. Any hidden variable that wanted to conspire to fake the results would have had to set its plan in motion before that starlight began its journey, an event that occurred before our planet even existed. This uses the vastness of space and time as an ultimate shield against any local conspiracy. Another idea uses the random polarization of starlight from two different stars to set the measurement bases. If the results still show that perfect, instantaneous correlation, it would mean that quantum entanglement held fast. The particles remained linked. even when the choice of how to test them was dictated by celestial bodies separated by a cosmic gulf. These experiments transform the entire sky into a laboratory. They are not just testing a theory. They are probing the universal validity of quantum mechanics itself, asking if its bizarre rules apply with the same force across the entire observable universe, from our backyard to the most distant quasars. If these cosmic tests confirm entanglement, it would mean this spooky connection is not just a local quirk of our planet. It is a fundamental feature of reality, woven into the fabric of the cosmos on the largest scales imaginable. The act of measuring an entangled particle is not a moment of destruction, but one of cosmic division. Within the framework of the many worlds interpretation, the wave function never collapses. It simply branches. At the instant you look at your particle, the entire universe splits into two distinct, equally real timelines. In one of these new worlds, you record a result of spin-up, and your colleague, light years away, finds their particle has spin down. In the other, brand new branch, a different version of you sees spin down while that version of your colleague sees spin up. Both outcomes are actualized, but they are forever separated, playing out in parallel universes that cannot interact. From this perspective, the spooky connection is demystified. There is no faster-than-light signal because there is no need for one. You and your counterpart are always in branches of reality that are perfectly consistent with the original entangled correlation. The link itself never severs. Instead, it acts as the blueprint, the fundamental rule that governs how the multiverse fractures with each observation. This replaces the unsettling randomness of collapse with a strange, sprawling determinism. Every possible outcome dictated by the quantum state does in fact occur. The mystery then shifts from a question of physics to one of identity. Which branch contains the real you? The answer, unsettlingly, is that both do. Your conscious experience simply follows one path, while another copy of your awareness, just as valid and real, follows the other. This interpretation trades the ghostly paradox of action at a distance for an infinitely multiplying cosmos, a reality where every quantum choice spawns a new universe, and every entangled connection is an eternal thread in the fabric of an ever-expanding multiverse. So if the universe constantly branches, why does our experience feel so singular and stable? A compelling answer may lie in a process of quantum natural selection. The theory of quantum Darwinism proposes that our solid, classical reality emerges not from a special act of consciousness, but from a kind of information ecology. When a quantum system, like an entangled particle, interacts with its environment, it does not just decohere quietly. It broadcasts its state to the world. Imagine looking at a simple object, like a coffee cup on your desk. The cup is constantly bouncing photons off its surface. Each of those scattered photons carries a tiny piece of information about the cup's location, its shape, its color. Those photons fly off in all directions, imprinting that same data onto countless air molecules and dust particles. Very quickly, the environment becomes flooded with redundant copies of the fact that the cup is right here. Your brain does not access some mystical, direct reality of the cup. It simply samples this stable, widely available information from the environment. You see the cup here and not over there because that particular piece of information has been massively replicated and has outcompeted all other possibilities. It has been selected for its stability. Now apply this to our entangled pair. Before measurement, the system is in a superposition of states. But the moment it interacts with a measuring device or even a single photon from the surrounding environment, that interaction creates multiple copies of information about its state. One particular outcome, say spin up, gets redundantly encoded into the environment faster and more robustly than its alternatives. That specific branch of the wave function becomes the dominant piece of data in the information ecosystem. All other potential outcomes are still there in the full quantum description, but they become effectively invisible to any local observer because they are not being broadcast. They are like a whisper drowned out by a roar. This explains why you and I, both local observers sampling the same environment, agree on a single objective outcome for the entangled particles. We are not causing the collapse. We are both reading from the same publicly available script that the environment has written and distributed. The fragile, global entanglement of the original pair is destroyed, replaced by a new, classical correlation that we all can see and agree upon. Quantum Darwinism bridges the profound gap between the weird quantum underworld and the familiar classical stage. It suggests that the objective world we share is not fundamental. It is a consensus reality, a stable plateau that has been selected for its ability to produce reliable, redundant information. The spooky connection of entanglement does not vanish. It is simply submerged, its coherence dissipated into the environment, leaving behind the clear, definite facts that form the bedrock of our everyday experience. This fragile quantum whisper, which we must shield with billion-dollar superfreezers, might be thriving inside a living creature. The European robin, a small bird that migrates thousands of miles, performs a navigational feat that has long puzzled scientists. It seems to see the unseen, navigating using the Earth's faint magnetic field as a visual map. The secret may lie not in a conventional compass, but in a quantum mechanism within its very eyes. The leading theory points to a molecule in the bird's retina that, when struck by light, creates a pair of molecules with unpaired electrons, known as a radical pair. These two electrons have a property called spin, and they are born into a special relationship. They are entangled. Their spins are perfectly correlated, dancing in a synchronized quantum state. The incredibly weak pull of the Earth's magnetic field acts like a subtle director, influencing the tempo of this dance. Depending on the field's orientation, it dictates whether the electron pair stays in a long-lived singlet state or quickly transitions to a triplet state. This quantum spin state then triggers a cascade of chemical signals, ultimately painting a perception of the magnetic field directly onto the bird's visual field. The world might literally look different to the robin, with shades of light or dark overlaying its vision, providing an intuitive compass heading. This radical pair mechanism suggests that the bird's brain is not processing the field, but experiencing it, using a biological sensor built from the spooky link between two electrons. The implications are staggering. A living system, warm and wet and seemingly chaotic, is potentially maintaining a delicate entangled state long enough to guide a journey across a continent. If quantum entanglement is at work here, it means nature has been an expert quantum engineer for millions of years. The mystery deepens when we look at the very foundation of life's energy. Inside every green leaf, within structures called photosynthetic reaction centers, sunlight is converted into chemical energy with near-perfect efficiency. Classical physics struggles to explain how the energy from a captured photon finds its way to the reaction center so flawlessly. The prevailing theory suggests it does not travel like a pinball bouncing through a maze. Instead, it may explore all possible paths at once. The energy exists as a wave of possibility, a quantum superposition that can simultaneously sample multiple routes through the complex molecular forest. It is a coordinated quantum search, using interference to cancel out the inefficient paths and reinforce the perfect one. This process, known as quantum coherence, is the same delicate phenomenon that underpins entanglement. For a fleeting moment, the entire system acts as one connected quantum whole, ensuring the energy arrives where it is needed without wasteful detours. The idea that the vibrant green of a forest is powered by quantum effects is a profound revelation. How is this possible in the warm, messy environment of a living cell? This is the central puzzle of quantum biology. Evolution appears to have found ingenious solutions. It may use molecular architectures that act as protective cages, shielding the quantum state from disruptive noise for just long enough to be useful. It might exploit rapid processes that complete their quantum task before the surrounding chaos can destroy the coherence. The line between the inanimate quantum world and the bustling reality of life begins to blur. We are forced to consider a breathtaking possibility. The spooky action at a distance is not confined to our labs. It might be flitting through the eyes of a migrating bird and buzzing within the leaves of every tree, a hidden ingredient in the ancient, elegant machinery of life itself. These fundamental rules are the invisible architecture that keeps the quantum world from descending into chaos. They are known as the No-Go Theorems, and they define the absolute limits of what entanglement can and cannot do. We have already met the No-Communication Theorem, the guardian of cosmic speed limits that prevents us from sending faster-than-light messages. Its partner in crime is the No-Cloning Theorem, the law that makes quantum cryptography possible. It states a simple, profound truth. You cannot create a perfect, independent copy of an unknown quantum state. Think of it like a unique, priceless snowflake. You can look at it, you can measure it, but in that very act you change it. You cannot faithfully duplicate its exact, fragile quantum configuration without destroying the original. This is not a technological hurdle. It is a fundamental law of nature, a built-in copyright protection for quantum information. This principle extends even further with the no-deletion theorem. Just as you cannot copy an unknown quantum state, you cannot perfectly erase one either. Information in the quantum realm is stubbornly persistent. It can be scrambled, it can be hidden, but it cannot be utterly annihilated. This trio of rules is underpinned by an even broader, more powerful constraint, the no-signaling principle. This is the ultimate guarantee of causality. It ensures that the probabilities for what you will see in your local measurements can never be used to transmit a single bit of information from a distant partner. When you measure your entangled particle, the outcome is always completely random, 50-50, no matter what anyone else does with their particle. You cannot tell from your local statistics alone whether someone far away has measured their particle or not. The spooky connection is there, but it is entirely private, a correlation that only reveals itself in hindsight. These theorems are not limitations in the sense of something we might one day engineer our way around. They are the rules of the game, the fundamental laws of quantum information processing. They define the playing field itself. Understanding these boundaries is just as crucial as celebrating entanglement's powers. They are the reason the universe, for all its profound weirdness, remains logically consistent. They prevent paradoxes, they uphold cause and effect, and they ensure that this incredible, non-local connection remains a silent, unbreakable bond rather than a cosmic telephone line. This leaves us staring into an abyss of questions far deeper than physics. Quantum entanglement is not just a scientific discovery. It is a philosophical earthquake that shatters the very foundations of what we call reality. For centuries, we have operated under an assumption known as local realism. It is a beautifully simple, intuitive view of the world. It says that objects have definite properties whether we are looking at them or not, and that no influence can travel faster than the speed of light. This is the bedrock of our everyday experience. A tree falling in a forest makes a sound, even if no one is there to hear it. But entanglement forces us to abandon this comforting picture. The experimental verdict is in, and it is unequivocal. We cannot have both locality and realism. The universe refuses to be both local and real. So what are we left with if we must choose? One possibility is that there is no objective reality independent of our measurements. The act of observation is not a passive reading of a pre-existing fact. It is an act of creation, bringing a specific property into being out of a cloud of potential. The moon is not there when nobody looks. as the physicist John Wheeler once provocatively suggested. Alternatively, we might have to accept that the universe is fundamentally non-separable. This is a profound idea. It means that the whole is more than the sum of its parts. You cannot understand a system by breaking it down into isolated, independent components. The entangled particles are not two separate things that then become linked. They are a single, unified entity that our classical minds, trapped in space and time, perceive as two distant objects. This challenges our most cherished notions of causality. How can one event cause another if there is no clear before and after? If the connection is instantaneous, and the particles were never truly separate to begin with? The very idea of an objective world, a universe that just is, begins to dissolve. The observer can no longer be a detached spectator peering through a microscope. They are an inseparable participant in the drama of reality. This radical shift in worldview, forced upon us by laboratory results, finds a strange and beautiful resonance in ancient Eastern philosophies. The Buddhist concept of dependent origination, which holds that all phenomena are interconnected and have no independent existence, echoes this quantum vision of a relational universe. We are moving from a cosmos of separate, solid things to a cosmos of dynamic, flowing relations. The fundamental stuff of reality may not be matter or energy, but relationship itself. This is not a small adjustment. It is a complete overhaul of our metaphysical map, suggesting that our deepest sense of being a separate self in a world of other objects may be the grandest illusion of all. The next great leap in our quantum journey will take us into the realm of the massive and the cosmic. For decades, we have entangled the smallest particles, photons, and atoms, but now the goal is to weave this spooky connection into objects large enough to be seen with the naked eye. Imagine a tiny glass bead, levitated in a perfect vacuum by laser light, being placed into a quantum superposition. It would not be in one place, but in two places at once. Then, a second bead would be entangled with the first. The profound question is whether gravity itself, the curvature of spacetime, acts as a constant, universal measurement device. Some theories, like gravitational decoherence, suggest that the sheer mass of an object and the gravitational field it generates could be the ultimate source of quantum collapse. By attempting to entangle these nanoparticles, we are not just testing a theory. We are probing the mysterious boundary where the quantum world of possibility is forced to become the classical world of fact. We are asking if gravity, the architect of galaxies, is the very force that erases quantum weirdness from our daily lives. This is a direct assault on one of the deepest unsolved problems in physics. Beyond the lab bench, the next laboratory is Earth itself. Satellites in orbit, like the Misch's satellite, have already demonstrated quantum key distribution from space. The next step is to use these orbiting platforms to test entanglement in the curved spacetime around our planet. According to Einstein's general relativity, gravity is the warping of space and time. A photon falling towards Earth experiences a slight shift in its frequency, a gravitational redshift. When two entangled photons take different paths through this curved spacetime, one traveling upwards and one downwards, does the gravitational field affect their spooky connection? Does the fabric of the universe itself leave a fingerprint on quantum correlations? These experiments will explore the subtle interplay between our two most powerful and seemingly incompatible theories of reality. The ultimate dream, however, lies even further out, at the edge of theoretical possibility. Could we ever entangle two black holes? The holographic principle and the ER equals EPR conjecture suggest that black holes are perhaps the most entangled objects in existence, their interiors connected by spacetime bridges. Observing this directly is beyond our current reach, but the very idea forces us to confront the nature of the singularity, that point of infinite density where our laws of physics break down. Perhaps entanglement is the key that will allow us to peer into that darkness, to ask what happens to information that falls into a black hole, and whether the fabric of space and time is truly fundamental or merely a holographic projection. These are not just thought experiments for a distant future. They are the blueprints for a new kind of physics, one that will use the strange, instantaneous link between particles to test the limits of quantum theory itself. Every time we push entanglement into a new domain, we are not just confirming what we know. We are asking the universe a more profound question, and the answer may finally reveal the unified theory that has eluded us for a century. This strange defiance of time finds its most dramatic expression in the quantum eraser experiment. In this mind-bending setup, pairs of entangled photons are created and sent on separate journeys. One photon, called the signal photon, races directly to a detector. Its journey is recorded and its path is seemingly fixed in the data. The other photon, the idler, is sent on a long, leisurely detour. It takes a scenic route through a maze of optics, ensuring it arrives at its own detector much later than its partner. The crucial choice comes with this idler photon. The experimenter can measure it in one of two ways. The first way forces it to reveal which path its signal partner took, cementing that partner's history as a particle with a definite trajectory. The second way of measuring the idler erases that path information, scrambling any record of a specific journey. Now for the part that bends the mind. The choice of how to measure the idler photon is made after the signal photon has already been detected and its data recorded. Yet, when scientists look back at the already collected data from the signal photon, they find something astonishing. If the idler was measured to erase the path information, the signal photon's data shows a wave-like interference pattern. It behaved as if it traveled all paths at once. But if the idler was measured to reveal the path, the same signal photon data shows a particle-like pattern, proving it took one specific route. The choice made in the present about the idler appears to reach back in time and dictate how its partner behaved in the past. This is not about sending a message backward. No one can use this to change a historical event or prevent a mistake. The randomness of the outcomes prevents that. Instead, it reveals a profound truth about quantum systems. The past is not a fixed, unchangeable ledger. It is a potentiality that is not fully settled until all the information from the present is in. The universe, it seems, does not commit to a single history until the final measurement ties everything together in a consistent whole. Our classical idea of a linear, cause and effect timeline shatters against this quantum reality, leaving us to wonder if the past itself is a story we are still writing. From a ghostly paradox in Einstein's mind to the humming heart of a quantum computer, our journey reveals a cosmos stitched together by invisible threads. This instant connection that defies distance has been transformed from a philosophical curiosity into the engine of a technological revolution, powering unbreakable codes and computers that can dream in parallel realities. It has forced us to abandon the comforting solidity of local realism, trading a universe of separate objects for one of dynamic, flowing relations. The spooky action is not an anomaly. It is a fundamental feature of our world, a whisper of a deeper, interconnected reality where space and time are not the final stage, but may themselves emerge from a vast, underlying network of quantum links. As we stand at this threshold, peering into the quantum era, we are doing more than just learning new physics. We are actively rewriting the story of existence, one entangled particle at a time. This is just the beginning of the conversation. If this exploration has reshaped your view of reality, share your thoughts in the comments below. Subscribe for more journeys into the mysteries of the cosmos, and always remember, the universe is far stranger and more wonderful than it appears.